So let's say we have a pipe again. This is the opening, and we have fluid going through it, and the fluid is going with a velocity of v1. The pressure entering the pipe is p1, and then the area of this opening of the pipe is a1. And then it's a pipe, and it can even go up. So it goes up, and the other end is actually even smaller. And let's say that the fluid, the liquid, is exiting the pipe with velocity v2. The pressure that it exerts as it goes out, let's say if there was like a membrane on the outside, how much pressure it would exert on it as it pushes it out or whatever, or on the adjacent water, is p2. And the area of the smaller opening, it doesn't have to be smaller, is a2. And let's say that this opening is at a height of, I don't know, let's say this opening is at a height on average of h1. And let's say that this opening, so the water exiting this opening, is on average at a height of h2. And we won't worry too much about the differential between the top of the pipe and the bottom of the pipe, because we'll assume that these h's are much bigger relative to the size of the pipe. Let's say that this is h2. So with that setup, and remember, there's fluid going through this thing. It's fluid going through this thing. So with that setup, let's go back to what would keep showing up, which is the law of conservation of energy, which is in any closed system, the amount of energy that you put into something is equal to the amount of energy that you get out. So energy in is equal to energy out. Well, what's the energy that you put into a system, or that the system starts off with at this end? Well, it's the work that you input plus the potential energy at that point of the system, plus the kinetic energy of that at that point of the system. And then we know from the conservation of energy that that has to equal the output work plus the output potential energy plus the output kinetic energy. A lot of times in the past we just said that the potential energy input plus the kinetic energy input is equal to the potential energy output plus the kinetic energy output. But we could also, the initial energy in a system can also be done by work. So we just added work to this equation that says that the energy in is equal to the energy out. So with that information, let's see if we can do anything interesting with this pipe that I've drawn. So what's the work that's being put into this system? Well, work is force times distance. So let's just focus on this. It's the force in times the distance in. And let's say that, so over a period of time t, what has been done? So we learned in the last video that over a period of time t, the fluid here might have moved this far. And what is this distance? This distance is the input velocity times whatever amount of time we're dealing with, so t. So that's the distance. And then what's the force? Well, the force is just pressure times area, and we can figure that out by just dividing force. We could divide this F by area and then multiply by area, so we get input force divided by area input times area input, right? And just divided and multiplied by the same number, and that's pressure, that's area, is equal to the input distance over that amount of time, and that's velocity times time, times velocity input times time. So the work input is equal to, so the work input is equal to pressure, the input pressure, times the input area, times the input velocity, times time, right? And what is this area, times velocity times time, times this distance? Well, that's the volume of fluid that flowed in at over that amount of time, right? So that equals the volume of fluid over that period of time. So we could call that volume in, or volume I. I keep switching between the 1 and the I. But that's the input volume, right? And we know what? We know that density is just mass per volume, or that volume times density is equal to mass. Or we know that volume is equal to mass divided by density. So the work that I'm putting into the system, I know I'm doing a lot of crazy things, but it'll make sense so far. The work that I'm putting into the system is equal to the input pressure times the amount of volume of fluid that moved over that period of time. And that volume of fluid is equal to the mass of the fluid that went in at that period of time. So we could call that the input mass divided by the density, right? Hopefully that makes a little bit of sense. And as we know, the input volume is going to be equal to the output volume. So the input mass, because the density doesn't change, is equal to the output mass. So we don't have to write an input and output for the mass. The mass is going to be constant. In any given amount of time, the mass that enters the system will be equivalent to the mass that exits the system. So there we go. We have an expression, an interesting expression, for the work being put into the system. What is the potential energy of the system on the left-hand side? Well, the potential energy of the system, potential energy input, is going to be equal to what? It's going to be equal to that same mass of fluid, right, that I talked about, same mass of fluid, times gravity, times this input height, the initial height, times h1. And what's the initial kinetic energy of the fluid? Well, that equals the mass of the fluid, this mass right here, of that same cylindrical volume that I keep pointing to, times the velocity of the fluid squared. This is just, we remember this from kinetic energy, divided by 2. So what's the total energy at this point in the system over this period of time? How much energy has gone into the system? Well, it's going to be the work done, which is the input pressure. I'm running out of space. Actually, let me erase all of this, and I'll probably have to run out of time too. That's okay. Better than being confused. Let me erase all of this. I don't want to erase everything. Dum-da-dum-da-dum-da-dum. Hope I'm not boring you. Okay, we're ready to go now. So back to what we were doing. So the total energy going into the system is the work being done into the system, and I rewrote it in this format, which is the input pressure, we'll call that P1, times the mass divided by the density of the liquid, whatever it is. So this is work in, plus, and what's the potential energy? Well, I wrote it right here. That's just mgh, where m is the mass of this volume of fluid. H is its average height. You can almost think of the center of mass. How high is the center of mass above the surface of the planet? Since we have a g here, we assume we're on Earth. So this is h1, because the height actually changes. So this is potential energy input plus the kinetic energy, mv1 squared over 2. So that is the kinetic energy input, right? And we know that this has to equal the energy coming out of the system, right? So let me clear up some more space here. Now that we wrote all that down neatly, I can get rid of it on this side, and we'll have space for our equations. I didn't have to delete this. I probably won't use this space up here. So this is going to be equal to the same thing on the output side, right? So this is going to be equal to the work out, so that'll be the output pressure times the mass divided by the density, plus the output potential energy, which will just be mgh2, plus the outbound kinetic energy, which would be V2 squared divided by 2. And I just realized I'm out of time, so I will continue this in the next video. See you soon.